Okay, we come to the Wheatstone bridge. Okay, section. What is Wheatstone bridge? Right. Last time we talked about the series and parallel circuit. Right. Just common circuit. We talk about Kirchhoff laws, KCL, KVL, Ohm laws. Right. And we use still we are on the resistive circuit. Right. Only resistor, no capacitor and no inductor. Okay, and with stone bridge is some application. Is one of application of the resistive circuit, right? Using the knowledge that we have learned. Okay, and the Wheatstone bridge is a resistive circuit that is frequently encountered in variety of measurement circuit, right? Measurement circuit. In general form, the bridge circuit is shown in this figure. Okay, here. This type of circuit we call Wheatstone bridge. Okay. Where R1, R2, R3 are known, right? So we know this value. We know this value. We know this value. And Rx is unknown. Okay, Rx is unknown resistance. So we can determine the resistance of Rx by this circuit. For example, if we know R1 is 10 ohm, R3 maybe 10 ohm, R2 we put is 20 ohm. And we measure the voltage between VA and VB. We can obtain Rx, okay, by calculation. Okay, by calculation. And this circuit is very popular in the measurement circuit. When Rx is a kind of sensor, okay, you know sensor. Sometimes we measure temperature and transfer into resistance, right? Some sensor transfer temperature to resistance to ohm. Some sensor transfer the pressure to ohm, right? Some sensor transfer the position to ohm, for example. So by using this type of circuit, we can we know the value of this sensor. And then, for example, if the sensor is maybe a degree Celsius to ohm, right? Maybe far away the sensor. We have winding to the sensor, and then when we measure Rx, then we know the ohm of the sensor, and then we can know the temperature, right, of that area. So this we can use this voltage to show the temperature, for example, okay, by using this circuit. Okay, okay. So how to calculate this circuit? Okay. This circuit can be written on this form. Okay, and the key index is the voltage between A and B. Okay, for Wheatstone bridge, right? The voltage between A and B. Okay, that can represent Rx. Okay, can represent Rx. Okay. Okay, the objective is to determine the Rx. Okay. Find the value of voltage. VAB is VAD minus VBD, right? By using KVL, right? KVL. VAB, the voltage between A and B is VA minus VB, right? And D is reference. For example, it's VAD and VBD, right? It's the difference between VAD and VBD. Okay. Here. And the source is Vs here, right? Or we can write VAB is VA minus VB if we make D as reference or zero voltage. Right? is VA minus VB. Okay. For example, if R1, R2, RT is 1 k ohm and Vs is 12 volt, VAB is 12 millivolt. How can we determine the Rx? Okay. So in case we know that R1 is 1 k ohm, R3 is 1 k ohm, R2 is 1 k ohm, and Vs is 12 volt, and we measure VAB at 12 millivolt. What is Rx? Okay, we can just determine Rx. It's not very difficult, right? You can use your knowledge to get Rx. Okay, okay. And one way to get the Rx that we can use voltage divider. We know that if I say this is V1, this is no, VAD, maybe VAD. The voltage across R2 is VAD. VAD would be VAD is Vs multiply R2, right? Divided by R1 plus R2. We learned about this voltage divider last time, right? Last week, right? I don't know. Do you remember? I think you remember, right? Okay. And also the voltage across Rx is VBD, right? VBD. VBD will be Rx divided by R3 plus Rx. Okay, here. And the difference between AD and BD would be VAB. Is this the difference between these two values, right? So we can move VS outside the bracket, right? Here we can get Vs into R1 plus R1 divided by R1 plus R2 minus Rx divided by R3 plus Rx here, right? Then we substitute VAB that we know is 12 millivolt here, 12 millivolt, 0.012 volt, right? And Vs is 12 volt. We substitute R2 at 1 k ohm, R1 1 k ohm, R2 1 k ohm, 1 k ohm, and we can solve for Rx, right? From this equation, we can solve from Rx. Here, this is the stone bit. Okay. On the other hand, if we use this circuit for measurement, we just let Rx vary, right? It will vary depending on degree Celsius or depending on the pressure, right? Depending on the sensor property. This is a variable resistor, okay? And we measure the voltage between A and B, right? VAB will represent the value of Rx, okay? Because VAB is depending on Rx here, right? Just scale our meter. Okay. So if we connect the circuit like this, this Vs, V1, V2, V3, sorry, R1, R1, R2, R3, Rx, A, B. Okay. Rx is unknown. Okay. And if we vary one resistor, for example, if R3 is variable resistor, if we vary the resistance until VAB equal to 0, If VAB is 0, it means that V across R1 and the voltage across R2 are the same, right? The voltage V1 and V2 is equal, right? And V3 and Vx also equal, right? And if we apply the voltage divider, it means that V1 is Vs into R1 divided by R1 plus R3, right? And V2 is also Vs into R2 divided by R2 plus Rx, right? So in this case, it means that the ratio between R1 and R3, R1 and R3 will equal to R2 and Rx, right? Okay, it will be equal. It means that if we use R1 and R2 at the same value, what mean? For example, if I use R1, 1k ohm, R2 is 1k ohm, and we vary R3 until VAB is 0. Okay, you catch the point? If I vary R3 until VAB is 0, and R3 is 1.2k ohm, what mean by Rx? So we know that Rx is, it means that Rx will be 1.2k ohm. You understand that? We just vary this resistance. Okay, we can measure Rx, right, by this connection, and we put the voltmeter here, right, and we adjust R3 until VAB is 0, right? If we adjust R3 until VAB is 0, it means R3 will represent Rx, right? Okay, so by this knowledge, we can measure the unknown value of resistance. Okay, we can measure unknown value of resistance. Okay, okay. Any question? No, right? Very well understand. No question. Okay, so this is just to check your understanding, right? This is what I taught. Okay, you can see this slide by yourself again, right? Okay, so let's see some example on the Wheatstone bridge. Uh, we have one common measurement device known as stand gauge. Stand gauge is the device that to measure the weight or the pressure. If we place the force on this sensor, the resistance will change. Okay, if we place the force, right, into this type of sensor, its resistance will change. Okay, we call this type of stand gauge. We will see this type of measurement uh, maybe at the torque sensor of the motor. Torque sensor of the motor. We would like to know how much the motor torque. We, if we would like to know maybe at the under the floor of the elevator, okay, we put stand gauge under the floor of elevator. When the weight is over the capacity of the elevator, it will send the alarm, right? We can measure the weight. If you could get into the elevator too many people get in the elevator, what happens? The elevator will take alarm, right? We take alarm that is sent by this type of the sensor. Okay, this type of sensor. So its output is the in ohm in resistor. Okay, so we know that the resistance of the material is represented by the range divided by the conductivity into area, right? Or sometimes we use resistivity, rho L divided by A, right? And if you sigma is conductivity, right? And we can write it in the term of resistivity, right? Okay. And then we can define gate factor or GF. GF is delta resistance, the change of resistance due to the change of length. Okay. Delta R by R divided by delta L by L we call gate factor. Okay. Yeah. And we have the epsilon, right? As a fractional change in length, delta L divided by L we call epsilon strain, epsilon. And then the change in resistance due to the applied strain, okay, will be delta R is the R, original R, multiplied with the gate factor and multiply with this epsilon, right? By this formula. Okay. So R0 is the resistance of the stand gate under no force, right? No strain. Because zero strain is just not no force applied to this sensor. And the value of GF for resistance strain gate made of metal foil is usually about 2. Yeah, about 2 is a uh, constant, right? Constant variable, right? Of each case is a constant variable. And this is the structure of the uh, metal foil stand gate. And uh, this type of sensor will have the variable resistance due to the force applied to it, right? This metal foil resistance here. And the epsilon or delta L by L, right? Delta L by L is about this value for 120 ohm gauge, right? It's just example. You don't need to remember. You don't need to try to remember. Just example, right? Just example of actual practical equipment. Okay, device. Just practical device. Okay. Okay. Here this is the photo of stand gate, right? We can put this gate here, and this is what is this circuit? What is this circuit? Wheatstone bridge, right? This is Wheatstone bridge, and this voltage can represent the resistance, right, of the gauge, right? This is the case is in the case maybe put when using in the industrial, we put this gauge in this maybe in some coal like this, right? Or we can have 4 strand gauge connect in bridge circuit, okay, connect in bridge circuit. Yeah. Okay. So if we have 4 resistance, 4 variable resistance, right? Connect like this, okay, like this, and put it in one uh, uh, surface, right? One beam, right? Put it in a beam here. This is a cross beam cross section W and H like this, and this is the resistance R1, R4 is here, R1, R1 is here, R4 is here, right? And R3 and R2 is on this surface, in the bottom surface like this. What happens if we apply the force here? The body will bend, right? The body will bend, and R1, this is the length increase at the upper surface, and the range decrease for the lower surface, right? Okay, the range will increase for upper surface and is decreased at the lower surface. Then R1 will increase, R4 is increased, R3 decrease, and R2 decrease, right? Okay, then it will cause VAB to change, right? VAB will change, right? Then VAB can represent how much the force applied to this material. Okay, and we can measure VAB that represent this force, right? Represent this force. Okay. So at the first, R1 and R4 is equal, and if it's bent, it will increase by delta R. And for R2 and R3, it will decrease by delta R. Okay. It's become R original R0 plus delta R, and R0 minus delta R, right? And R0 is the zero state resistance of the gate, right? Is the force F applied here at the distance L from the cantilever beam. This is the strain can be computed by 6 LF divided by W. W is the Y. H is the height of this the body, right? Here. And Y is the beam modulus elasticity. Here is the modulus elasticity. Then we can calculate this circuit, right? IA is Vs divided by R1 plus R2. IB is Vs divided by R3 plus R4, right? Because the voltage across R1 plus R2 is Vs. Across R3 plus R4 is also Vs, right? Like this. And VA. VA is this voltage, right? IB R4 is VB minus IAR2. IAR2 is here. Sorry, it should be VO is here. VO is here. Right? It should be VAB. VO is VAB. VB minus VA. VO is VB minus VA. So this is VB. This is VA, right? And then we substitute IA here and IB here, right? We get this formula, right? By arranging this formula, and R4 become during the force applied, R4 become R0 plus delta R, right? And R1 also. R2 and R3 become R0 minus delta R. Right? Then we substitute R0 plus delta R and R0 minus delta R for R1, R4, R2, R3 respectively. Right? Here. Okay, then we can just rearrange these into this form, right? It's become delta R divided by R0. And delta R by R0 is GF epsilon here, right? GF epsilon. And then we substitute epsilon by this formula. Finally, VO become constant, right? This is a constant into the force. Okay, so we measure the voltage between VA and VB can represent the force, right? It's the constant multiplied with this force. So VO is just proportionally, right? Vary to F. Right? By this connection, we can measure VO that represent the force, right? Okay, just like that. Okay. This is maybe you can try some calculation, right? With this formula, just substitute the constant value in this slide, okay, to make you more understand, right? Yeah. Okay. Now we come to some practical voltage and current source, right? Surely in this in this class, we will calculate under ideal source, mostly under ideal source. But in practice, the source usually have internal resistance, okay? Internal resistance. For example, if you have the battery, 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 plus, minus, if we connect with maybe 10 ohm, 1.5 volts, we calculate it as 1.5 volt. But in fact, when the battery take the load, right, take the current, there is the internal resistance here. R source, we call R of resistance of the source. When the current flow, right, for example, if the resistance of the source 0.1 like this, the current flow plus to this resistance is will drop the voltage at the terminal. It will less than 1.5 volt here, right? The voltage will drop when we take the load because it's dropped to this resistance, right? It's dropped to the resistance, internal resistance. The more current flow, the more voltage drop. Okay, the more current flow, the more voltage drop. Yeah. Like this. In fact, if we calculate by consider the internal resistance, this will be just more detail of calculation. Okay, you get more detail and usually the internal resistance of the practical source is very low. Yeah, it's very low. So we sometimes we neglect this resistance. Okay, we can neglect this resistance. Yeah. Okay, this is a source. Okay, and also RS in this case it's very low for voltage source, but for current source RS is very big. Okay, very big. It means almost open, right? Open circuit here. Okay, similar to open circuit. Here. Okay, this is very big. It's open circuit. This is very small short circuit. Okay, so we just calculate as ideal source, right? Okay. Okay. And when we measure device, for example, ohm meter, we can use this ohm meter for measurement the resistance. Okay. Ammeter, if we put if we would like to measure the current, we put this symbol, right? It's means that ammeter. Usually ammeter have zero internal resistance, and the voltage we use voltmeter. Usually the resistance is very large, right? It's not affect to the circuit. Voltmeter, ammeter, we ideally not affect to our circuit, right? But in fact, when we put the voltmeter here, some small current will flow in practice, right? In fact, but we neglect this value. Similarly, for ammeter, usually some internal resistance will cause voltage drop here, right? But we consider it as the short circuit, right? Okay, I think you learned about galvanometer in physics, right? And to make it as ammeter and to make it as voltmeter, right? But nowadays we usually use digital multimeter, right? Ammeter and voltmeter. Okay. Anyway, okay, we can uh, if we consider the practical voltmeter, this the resistance will be here, but in usually we say it's very large. Right? Ammeter also is very small, it's very large, right? And also we can measure the power, right, by using amp and volt, right? Or we can call watt meter. This is we call watt meter. to measure the power. Okay. Okay, this is your homework of this slide. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Okay, 14 question for you, 14 topic. Just try to do it one by one. It's not really difficult, but it will increase your understanding. Okay, and it will help you for your exam. Right? So, how many days you need for doing this? 1 week. So next Wednesday, okay? 1 week, right? Next Wednesday we do. Next Wednesday. Next Wednesday is 14, right? Okay.
We submit of e-learning or get the precaution.
So it's depending on PR. Maybe she will provide the submission channel for you. Usually, in electrical engineering school, we submit homework to e-learning. So she will provide some homework channel. You can use e-learning, right? Okay, no problem. But you use your handwriting. Okay, your handwriting to solve the problem. It's good practice for you. And then you may take a photo, okay, to the file and you submit to e-learning. Okay, any question so far?